तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we have been discussing the bipolar junction transistor. In the previous lecture, we started explaining the common emitter current voltage characteristics. Okay, let us look at the slide which we were trying to explain. So, we want to explain these family of curves. In fact, we started with a single curve. We took one of these curves and then we qualitatively explained how we get the various points on this curve. So, for example, this was the curve that we obtained. For one value of IB, we obtained this curve by plotting the excess carrier distributions for different voltage and current conditions. So, for VEC equal to 0, then for IC equal to 0, and then this point corresponds to VCB equal to 0, collector base voltage equal to 0. And then we went beyond this point and then we also arrived at an explanation why the current goes on increasing in this region instead of saturating. So, what we said is that the beta of the device goes on changing as you change your VEC. This is because of base width modulation. So, in fact, this was the formula for beta as a function of beta naught, where beta naught is the beta when collector base voltage is 0. Delta XB is the base width modulation, change in the depletion layer of the collector junction within the base, that is this quantity. This is the delta XB. This delta XB is also delta WB, because as this depletion region shifts, the base width also gets modulated. So, 1 minus delta XB by WB naught, where WB naught is the base width for collector base voltage equal to 0. Reciprocal of this quantity multiplied by beta naught is the beta for any collector base voltage. And then we made a calculation for the device in the solved example, and we showed that beta for a collector base voltage of minus 9 volts is approximately equal to 1.4 beta naught. Okay. So, this means that from VCB equal to 0 to VCB equal to 9 volts, the change in beta is 0.4 times beta naught. So, this is almost 40% of the value of beta. This is what we explained. So, if we try to put this information on this curve here, then it would mean that when you go to the point corresponding to VCB equal to minus 9 volt, then this change in current will correspond to 40% change in the beta. So, this is your delta IC, which is equal to delta beta into IB. We are neglecting the contribution because of IC naught. So, the equation is IC equal to beta times IB plus beta plus 1 times IC naught, and then you take increments, you neglect this part because this is small. When you take increments you get this information, this equation. So this is your delta IC. Okay. Now obviously this diagram is not to scale because this delta beta is 40% of beta naught. So in fact this value is beta naught into IB, okay, because this is Vcb equal to 0. So beta corresponding to this point is beta naught. So beta naught into IB, whereas this is beta times IB, and delta beta into IB is this increment delta IC. So this explains why the current does not saturate and it goes on increasing. Now in our slide here we do not find that much of increase in current. You take any one of these lines. So supposing you take the line corresponding to 36 microamps IB, the increment in the collector current from this point to this point is much less than what we have estimated here in the solved example. Okay. So here the change is 40%, whereas there the change appears to be only about some 10-15%. Okay, that is, this increment is some 10-15% of this in our slide. So this obviously means that the practical transistor for which those current voltage characteristics are obtained has a higher value of doping in the base. Okay, when the doping in the base is higher, then this delta XB will be lower, the modulation of the base width would be lower, collector base depletion region will be smaller. So therefore the beta will not change that much with collector base voltage. Okay. So this is how the base width modulation and the slope of these characteristics here is related to the doping in the base. Now proceeding further, we find that this curve is going to break down at some point. Now what is this breakdown point? At what voltage will this breakdown occur? This is what is the next point that we want to explain. Okay. Now to understand why the breakdown occurs, let us look at the picture inside the device. So this is your transistor, and let us say this is your collector to base depletion layer. So this is P plus plus, N plus and P. Now let us show the currents which are flowing according to the flow diagram. You have the whole current being injected, and if we neglect the recombination in the base, which is what happens in the modern transistor, in order to arrive at a simple picture we neglect that recombination in the base. So this current goes right through like this. So this is the whole current. Now there is a part of the whole current recombining here with the electron current which is injected. And there is an IC naught here, so that is shown generated current. So either it could be shown within the depletion layer, or it could be shown here outside. In fact, both these places there will be generation. Okay, so there will be generation within the depletion layer and there will be generation in the neutral region. So right now we are not bothered about exactly where the generation is, so we will just show the generation within the depletion layer, for example. So this is IC naught. So this electron current, these electrons move from collector to base, whereas here the electrons are moving from base to emitters. This is reverse biased, whereas this is forward biased. This junction is forward biased. And this, all these electrons, the base supplies the electrons. This is the picture below breakdown. Now, we know from the p-n junction theory that as you go on increasing the reverse bias across a junction, impact ionization within the depletion layer sets in, okay? And because of the impact ionization, the reverse current that is flowing through the depletion layer starts getting multiplied. So this now we will show here as follows. So this current, when it moves through the depletion layer, gets multiplied. So this we show as follows. So multiplied means electron hole pairs are generated. So the holes which are generated will move up and join these holes, whereas electrons which are generated will cross, something like this. So this is the additional current because of impact ionization. Now similarly there will be a multiplication of this current also, this whole current which is injected from the base to the collector. So here you have holes which are generated, which join up with these holes, and electrons which are generated which join here, okay. So let us show all this joining the same point. Okay, so these are the extra electrons which have come, okay, electron hole pairs which are generated because of multiplication. So impact ionization. Multiplication due to impact ionization. This is what is shown here, okay. So this and this. Now we need to see what is the result of this multiplication. We can write a simple equation to explain the effect of this multiplication. But before we write the equation, let us understand qualitatively why the breakdown occurs. See, please understand that breakdown means a sudden change in current, a rapid change in current. So here if you see carefully, what is happening is the following. Because of the multiplication in the depletion layer, you have extra electrons coming in which all join up along with the base current and IC naught, and all these electrons are getting injected here, okay. Now since this current is increasing because of impact ionization, this electron current that is injected from base to emitter is increasing because of impact ionization in the collector. This current, the whole current that is injected from emitter to base also increases, because you know the ratio of the whole current to electron current across a forward bias junction depends only on the ratio of the doping levels on both sides, and also on other parameters such as the diffusion coefficient, lifetime, and so on. So since these parameters are not changing here across on this side and the other side of the junction, ratio of the whole current and electron current, ratio of these two currents should remain a constant. Therefore if the electron current increases, the whole current here that is injected also increases. So therefore the current that is moving in here is increasing, and this increasing current is further getting multiplied, giving rise to more electron hole pairs, and these electrons again come back to the emitter they increase the whole current in turn. So you see there is what is called a positive feedback. Okay, there is what is called a positive feedback. Okay, so increasing current giving rise to more current, which further gives rise to more current, and so on. So there is a feedback from emitter to collector and collector to emitter. So this cycle sets in, and as this cycle sets in, the current starts increasing very rapidly. So this positive feedback, which is there because of the transistor action, because of the presence of a reverse bias junction in close proximity to the forward bias junction. Okay, so that is the reason why the impact ionization is causing a rapid change in current in the transistor, and this is what is the reason for breakdown. Now we can write this in the form of an equation as follows. So when there is no multiplication or impact ionization, then we can write as follows. So no impact ionization. Your equation is IC is equal to alpha times IE plus IC naught. That is this white line and this white line. Okay, this white line is alpha times IE. This is IE, and this quantity is IC naught, and this quantity is alpha times IE. So no impact ionization, IC is alpha IE plus IC naught. We know this equation because we have discussed this in the context of basic transistor action. Now, in the presence of multiplication, what is happening? This alpha IE current, this current is getting multiplied. So you have this additional current shown here by this yellow electron hole pair generation. Similarly, IC naught also is getting multiplied, okay, because of impact ionization. So in the presence of impact ionization, so with impact ionization, we can simply write the equation as IC equal to this quantity multiplied by M. So IC is equal to M into alpha IE plus IC naught, where M is the multiplication factor due to impact ionization. Okay, so this is a difference in the presence of impact ionization and between the situation in the presence of impact ionization and in the absence of impact ionization is this multiplication factor M. This M is equal to 1 when there is no impact ionization. Now please note that we must start with this equation and we cannot start with this equation in the presence of impact ionization. Okay, this equation is alright when the impact ionization is absent, but in the presence of impact ionization, okay, you cannot have IC as beta times IB plus this other current. This is because you can see here the situation has changed. You have additional electron current coming in because of the generation within the depletion layer because of this impact ionization. Therefore, that equation gets modified, so we should not start with that equation, we must start with this equation. Now when we write this equation, now you can easily transform this equation to show when the collector current will start increasing rapidly. For this purpose, we must write IE in terms of IC and IB, okay, because IB is being maintained constant. You can see here that when you are tracing this whole curve, your IB is constant, okay. So that is why we must express this IE in terms of IB and IC. When we do that, let us see what happens. So IC is equal to M times IE alpha IE plus IC naught, where this IE is IC plus IB. So we get IC is equal to m times alpha times IC plus IB plus m times IC naught. Now you shift this IC on this side, you will get 1 minus m times alpha into IC is equal to m times alpha into IB plus m times IC naught. In other words, IC is equal to m into alpha IB plus IC naught divided by 1 minus m alpha. Okay? So this is your equation for IC in the presence of multiplication. This equation shows the so called positive feedback action. Okay? In fact, one can easily correlate the form of this equation to the form of a feedback amplifier. Now we will not do it in this course, but when you do the feedback amplifier in the circuits course, you can easily see that this is the loop gain. M into alpha is the loop gain, M is a forward gain and m into alpha is the loop gain. So now coming back to breakdown, here we see that IC tends to infinity when m alpha tends to 1 in this new denominator, or this is same as saying m tends to 1 by alpha. So whenever m tends to 1 by alpha, multiplication is equal to 1 by alpha, which is, please note that alpha is very close to 1 but less than 1. So 1 by alpha is a quantity which is slightly greater than 1. So even if there is a slight amount of multiplication, what this shows is that the current IC will tend to infinity. Okay? Now this is what is happening here. At this point your multiplication is becoming equal to 1 by alpha, and at that point the breakdown occurs. Okay? So this is how you can trace a complete IC versus VEC curve for one value of IB. Now to complete the picture, we must trace the curve for another value of IB, okay, and for the condition IB equal to 0. Now what is the curve for the condition IB equal to 0? That can be seen very easily from here. Note that IC equal to beta times IB plus beta plus 1 times IC naught. This is valid in the active region. Okay? So this from here, that is VCB equal to 0 to breakdown, you have the active region, and this region is called the saturation region. Okay? This is saturation. Why is this called the saturation region? We will see shortly why the word saturation is used here. Okay, but right now let us return to the active region, and this is the equation. So if IB is equal to 0, your equation is IC is simply equal to beta plus 1 times IC naught. Okay? So IC is not equal to 0 when IB equal to 0. There is a small amount of IC flowing. So that will be the condition here. When IB is equal to 0, obviously IC will be 0 for 0 VEC, and here you will have something like this going. Okay? And of course this will break down. Now the breakdown voltage here is not the same as the breakdown voltage here for higher value of IB. This is, now we will remove these other things. This is for IB equal to 0. Breakdown voltage for IB equal to 0 is more than breakdown voltage for any other value of IB. This issue we will discuss separately. Okay, why this happens we will discuss separately. Now we just want to plot this curve for IB equal to 0. Okay, so this value is beta plus 1 times IC naught, the value of the current here. This current is beta plus 1 times IC naught. There is a small slope here, it is not exactly flat because beta is changing with VEC. Now let us plot for any other value of IB. Supposing we want to plot for a lower value of IB, okay, than this. Now obviously here what is going to happen is this point is going to shift up, okay, for a smaller value of IB. And what about this point? That point is also going to shift left, because for a smaller value of IB the collector base voltage equal to 0 condition, okay, when it occurs the emitter base voltage will be smaller. Okay, for small value of IB the emitter base voltage that you have to maintain to give the particular value of IB is smaller, right. So and since this is the emitter base voltage, for small value of IB the emitter base voltage is smaller, so your point will shift left. So we start here at a point which is higher because this IB is smaller, and then here we end up with a point that is lower because your IB is lower, beta times IB is smaller, and also this VEB is lower, okay, for a lower value of IB. Now when we join we will find that this curve will almost go through the same point. We will not discuss this issue in much detail because it is not so important. We have seen that these voltages are very, very small, okay. So in fact this is the curve for a lower value of IB up to the point where the saturation region ends. Now question arises, in the active region will the slope of the curve here, will it be more than this or less than this, okay. Will the slope here this is the slope, will this slope be more, will this be more than this or will this be less than this? Now it can be easily seen that this slope should be less as compared to this slope, because we have seen that delta IC is equal to delta beta into IB. So delta IC by delta VEC, which is the slope, okay, this is the slope here, this we can write in this form, and delta beta by delta VEC will not be very different for these two cases, okay, because when we estimated the delta beta, if you recall, we wrote down the fact that beta is equal to beta naught into 1 by 1 minus delta xb by wb naught. Now in entire calculation the IB didn't enter into picture. We found that delta beta depended only on the change in the collector base voltage, and since the change in the emitter base voltage is rather small because emitter base is forward biased, change in the emitter collector voltage is almost same as the change in the emitter base collector base voltage. So this quantity does not change much, okay, this is almost constant, therefore this ratio depends on IB, it is proportional to IB, therefore the slope will be smaller for a smaller value of IB. So this is very important, so you will find that for higher and higher values of IB your slope will go on increasing, okay, and then you will have a breakdown. Now as we said earlier, and this point now we will explain, the breakdown voltage goes on decreasing as your IB increases from IB equal to 0. Of course it decreases and then after some time it becomes constant and then it starts increasing again. So this change in the breakdown voltage with IB is happening because of the change in the beta as a function of IC. Okay. So as the collector current changes, the beta does not remain constant, it changes. So far we have been assuming an ideal bipolar junction transistor where the beta was independent of collector current. Okay. Please look at an equation for your beta. It contains various parameters, none of which depend on the collector current. Okay. So in practice, however, this is a non-ideality that for a practical transistor, beta depends on the collector current. Okay. And that is the reason why the alpha also depends on the collector current, and if you use this equation for breakdown, okay, that is m tending to 1 by alpha, then if alpha is a function of IC, m also is a function of IC. So breakdown will occur at different voltages for different values of collector current. Okay. Now this point we will discuss shortly. To summarize our discussion here, we can go to the slide. Now we have explained how your IB increases. When the IB increases, your collector current goes on increasing. For IB equal to 0, your current is beta plus 1 times IC naught, collector current. So when IB is equal to 0, and then the collector current almost increases linearly with base current. Okay. So that is how you have these increasing currents, and you find here that the slope of the characteristics goes on increasing. Okay. So you start with the lowest curve, you have a certain slope, whereas you find slope of this curve for minus 24 microampere IB is more than the slope of the curve for IB equal to 0, and finally slope of 60 microampere curve, IB equal to 60 microamps, this slope is more than this slope. So continuously the slope of the curves is increasing. This we have explained, okay, why this happens. And now let us separate the various regions of operation here. This region to the left of this dotted line is the saturation region, and between this dotted line and this dotted line here is the active region. Okay. And beyond this dotted line, to the right of this dotted line, is the breakdown portion. Now we want to explain why the breakdown voltage is decreasing here, okay, as your collector current is increasing. Now before we do that, let us shortly discuss why this region is called the saturation region. Why the word saturation? The reason for using of the word saturation is very simple. In that region, that is in this region here, collector base voltage is such that the collector base junction is forward biased. Okay. So saturation region, collector base junction forward biased. Now when collector base junction is forward biased, you have a large number of excess carriers injected into the collector. Okay. So that is why people say that the collector has got saturated with excess carriers when the collector base junction is forward biased. It is this large number of excess carriers for which we use the word saturation, right. So collector is saturated with excess carriers, and that is why the word saturation. Okay. So saturation region, because collector base junction is forward biased, and this implies large excess carrier concentration in the collector. Another way of saying the same thing is that collector is saturated with excess carriers. Now let us move to the explanation of the variation of the breakdown voltage with the collector current. For this purpose, let us look at this slide, beta versus IC characteristics. This slide shows how the beta changes with the collector current. So you find for small collector current the beta is low, and as you increase the collector current, the beta starts increasing. It reaches a peak at some value and then it falls again. Okay. So this curve has been shown for a particular value of Vce. You can have similar curves for other values of Vce. Why does this happen? Why does the beta change with IC? So beta changing with IC also means alpha changing with IC. Okay. So you can either explain variation of beta with IC, or we can explain variation of alpha with IC. So that is our next topic that we will discuss. So let us explain why alpha varies with IC. So look at your device again, the internal picture. Now we will show the emitter base and collector base depletion regions clearly. Let us show the currents. Now we will assume that the collector base voltage is 0 for simplicity, because to explain variation of alpha with IC we do not need the collector base voltage. So this is the picture. These are the holes, they are the electrons. We have neglected the recombination in the base because that is the situation in modern transistor. So therefore we write alpha, let us write it here, alpha which is equal to gamma into B, base transport factor, injection efficiency into base transport factor is approximately gamma itself for modern BJT. Particularly for small signal BJT, modern small signal BJT. So concentrate on injection efficiency. Now what is injection efficiency? Injection efficiency is equal to IEP by IE. So this is IE, this is IEP, and this quantity is IEN. For very low collector currents, what happens is the recombination in the depletion layer, which we have neglected, is significant as compared to this current. So for low currents the picture is this. This current is normally denoted IGR, generation recombination current. Okay. So when talking about PN junctions, we have explained this. Okay. Deviation of the characteristics of a PN junction from ideal diode characteristics. So real diode characteristics, they differ from the ideal diode characteristics in that you must take into account the generation recombination within the depletion layer. Okay. Now that becomes important when the collector current is low. So when you write this equation for gamma, this is equal to IEP upon IE is now equal to IEP plus IEN plus IGR. Okay. So IE is equal to this quantity plus this quantity plus this quantity plus IGR. So far we had neglected this IGR, okay, whereas if you want to find out the gamma at low currents, then IGR should be taken into account. That is why the gamma is low, and since gamma is low, alpha is also low. So alpha is small, alpha low at low IC due to IGR. Okay. Now at very high values of IC, again alpha is low, and that is because gamma is low. Why? So let us see why. So high IC, in this condition your gamma is again given by IEP by IEP plus IEN, because IGR is not so important. Okay, so this is low IC. Low IC IGR is important, but high IC IGR is not important. However, when you take the ratio, so this you can write as 1 by 1 plus IEN by IEP. So when you take the ratio IEN by IEP, this ratio IEN by IEP is not the same at very high currents and moderate currents. This is because of the fact that since base is lightly doped compared to emitter, at high currents there is high injection level in the base. When the injection level in the base is high, the amount of electron current that is injected from the base to the emitter, that current is more than what you calculate assuming low injection level in the base. Okay, this follows directly from the Boltzmann relation. So when you go to the P-N junction theory, okay, from there you can easily show that when the one region of the junction is in high injection level, the amount of current that that particular region injects into the low injection level region is higher. Okay, so the amount of IEN that is injected is higher as compared to moderate current conditions. So IEN by IEP ratio, this falls. I am sorry, IEN by IEP ratio rises, okay, for higher values of IC. So gamma falls for high IC due to increase in IEN by IEP, and therefore alpha also falls. So hence alpha falls for high IC. Okay, so we can now show this on a graph as follows. If you plot alpha as a function of IC, where IC is plotted on a log scale. Okay, so IC is plotted on a log scale. This is because you must show a wide range of IC. Okay, only then for very high IC and very low IC you can show the behavior. So the behavior looks something like this. This is for alpha. Okay, so both these regions, alpha is low because of low injection efficiency, here because of generation recombination in the depletion layer, here because of high injection level in the base. So generation recombination in emitter depletion layer. And beyond this, here it is high level in the base, high injection level in the base. Okay. Now when alpha changes like this, if you plot the change in beta, it will look something like this. Okay. So the change in beta appears, the beta appears to be changing everywhere, okay, on this IC axis, although alpha appears to be fairly constant over a wide range, right. This difference in shapes of alpha versus IC and beta versus IC has to do with the fact that beta is very sensitive to change in alpha. So even for a small change in alpha, there is a large change in beta. I leave it to you as an exercise to show. Okay, you write the equation, alpha is equal to or let us write beta. Beta is equal to alpha by 1 minus alpha, and then try to express d beta by dic as a function of d alpha by dic, okay, just by differentiating, and you can very easily show that even for a small change in alpha there is a significant change in beta. That is why even though in this range beta appears to be almost constant, the alpha appears to be almost constant, the beta changes, okay. So that is the reason for the variation of beta with IC or variation of alpha with IC. Now once we know this variation, we can easily explain why the breakdown voltage is decreasing when your collector current is rising, okay, to start with. So that is because here if you now look at the breakdown region, this region, the breakdown occurs when multiplication factor tends to 1 by alpha. Now alpha is low for low values of IC or low values of IB. So multiplication factor required for breakdown is higher, 1 by alpha is higher, so M is higher. As your collector current goes on increasing, your alpha goes on increasing, therefore multiplication factor required for breakdown goes on falling, therefore the breakdown voltage falls, okay. So this means that this region here corresponds to this region here, okay. So this is the region that we are talking about. We have really not shown the IC VC characteristics for this region, okay, that is a very high IC region. So the slide that we show here, okay, this collector current range that is shown is the range where the alpha is increasing with IC or beta is increasing with IC. So that explains why your breakdown voltage falls. So with this we have completed the explanation of the IC versus VC characteristics, okay. Now this the voltage corresponding to IB equal to 0, breakdown voltage corresponding to IB equal to 0, this is called Vceo, okay, or Vceo. Look at this slide again. This voltage is the Vceo. Why is it called Vceo? This means collector to emitter breakdown with base open, okay. So please note that IB is equal to 0 for that case, and 0 IB means the base is open, that is the transistor is connected like this, okay. So the base is open and this is the transistor connection. This is the condition, this is the bias when IB is equal to 0, okay. So we rub off all this to show the condition for IB equal to 0. Now IB is 0, okay. So that is why this breakdown voltage here is Vceo or Vceo, depends on how you show the axis, okay. Collector to emitter breakdown with base open. So in fact there are two types of breakdown. Let us look at this. Normally we come across a breakdown voltage called Vceo and a breakdown voltage called Vcbo. Now this Vcbo here is higher than Vceo. So what is Vcbo? This is collector to base breakdown with emitter open, okay. So breakdown voltage for this condition is much higher than breakdown voltage for this condition. Let us understand why. So this is for Vceo. For Vcbo, so when you are talking of breakdown, you normally use the B here. BV stands for breakdown. For BVCBO, the condition is as follows. So you have this transistor, the emitter is open, and you are measuring the breakdown voltage between collector and base. Okay. So this is VCE and this is VCB. This breakdown voltage VCBO is much higher than this breakdown voltage VCEO. Okay. What is the reason? The reason is very simple. This breakdown voltage is the breakdown voltage of the collector base junction. Okay. So it is as though there is no transistor action. Breakdown voltage of this device is the same as the breakdown voltage of this device because the emitter is open, which means the transistor breakdown is same as the PN junction breakdown. Okay. So here breakdown voltage occurs when multiplication in this junction reaches infinity at breakdown. Whereas here, as we have shown already, breakdown occurs when multiplication reaches 1 by alpha. So clearly you will need a higher voltage to make the multiplication factor infinity because of impact ionization, okay, than this case when you only have to reach 1 by alpha, which is very close to 1, a multiplication factor which is just more than 1. To reach that you need a much lower voltage. Okay. So this is the reason why breakdown voltage between collector and base with emitter open is much higher than breakdown voltage between collector and emitter with base open. In fact, there is a relation between the two which we can derive very easily as follows. For this purpose, we use an empirical relation for the multiplication factor due to impact ionization. The expression is M is equal to 1 by 1 minus voltage across the junction by breakdown voltage across the junction whole power m, where m normally lies between 4 and 6. Okay. This is an empirical relation for multiplication factor. You find that when the voltage becomes equal to breakdown voltage, this multiplication factor tends to infinity. Now using this basic relation for a PN junction, okay, let us see how we can express the relation between VCBO and VCEO. Okay. Now you go here, VCEO occurs when m tends to 1 by alpha, that is this quantity is 1 by alpha. So I write 1 by alpha at breakdown when the base is open. M equal to 1 by alpha equal to, so this quantity is 1 minus voltage that you are applying, that is Vc, that is a voltage across the collector base junction by the breakdown voltage of the collector base junction. Now breakdown voltage of the collector base junction we can write as VCBO. Okay, this breakdown voltage of the collector base junction is nothing but VCBO. Now we need to find out for what value of voltage this quantity will become 1 by alpha. Now this voltage here is the collector base voltage of this device in this particular configuration. This is very important. Okay. Please note that Vcbo is a breakdown voltage of the collector base junction when it is isolated. Okay. So which is same as the collector base breakdown when the emitter is open. That is why VBR is being replaced by Vcbo. But this V is nothing but the voltage across the collector base junction in this particular circuit configuration when the base is open. So if you add this collector base voltage to the very small value of forward bias across the emitter base voltage, please note that this is the polarity when you apply a voltage like this, reverse bias and forward bias. This is very small. So really the voltage here is approximately equal to this total voltage. That is why we can replace this by the Vceo, because at breakdown the voltage is Vceo. So this is a relation between Vceo and Vcbo. Okay? When you solve this, you will get Vceo by Vcbo is equal to one minus alpha whole power 1 by m. Now 1 minus alpha is nothing but 1 by beta plus 1, and therefore you have Vceo is equal to Vcbo by 1 plus beta whole power 1 by m. This is the relation between the collector to emitter breakdown voltage of a transistor when the base is open and the collector base breakdown voltage of the same transistor, right? So you can see what is the factor here. If you have beta is about 99, so 1 plus beta is 100, and if m is for example 4, then 1/4 root of 100, square root of 100 is 10, and then square root of 10. So you will have the Vceo as Vcbo by square root of 10. So Vceo can be as low as 1/3 of the Vcbo. Okay? So that is what is shown here on this slide. So note here that the Vceo corresponds to the condition IB equal to 0, but as your collector current in the device increases, your breakdown voltage falls because of change in alpha with IC, and in fact here a slight rise is also shown for very high collector currents. This is again because of fall in alpha. Okay? This region was not shown in our family of current voltage characteristics that we showed. So with this we have completed the output characteristics of the device in the common emitter configuration. We shall continue with some more aspects of the DC characteristics in the next class, following which we will discuss the small signal characteristics.